should be comfortable with the fact that A will be furthest downfield. Then I've got types B and C, and even though you can't really see it on the slide, blown up, I see that type B, which we predicted, would be a couple of closely spaced doublets. And here's a couple of even closer spaced doublets, which is type, where are we looking at there? That's C. Does that make sense? Now, fortunately for us, complex splitting that involves splitting trees is fairly common, but we don't encounter a lot. It's something that you just need to be prepared to interpret when it does happen. Now, it gets a little more complicated when we talk about stereochemical non-equivalence. If I, and what the textbook suggests, and this is commonly used technique, if I look at a series of hydrogens attached to the same carbon, if I replace one of them and it makes the other stereochemically different, then they're going to split each other. Now, and I don't know why they give you an example where that doesn't happen here to start you off, but notice if I replace one with a Z, these two are still identical. Okay, and so they don't split each other. If I replace 2 with a Z, these two are still the same. If I replace 3 with a Z, they're all the same. So these hydrogens are identical to one another, and they won't split one another. However, when we saw this a moment ago, and you may remember that double bonds, when I have cis and trans isomers, way back when we classified, they're also called diastereomers. Cis and trans isomers are considered diastereomers as well. So, hydrogens that upon being replaced create cis-trans isomers are called diastereotopic. That means they create diastereomers. So notice, here I've got a hydrogen or a carbon with 2 hydrogens here. This compound and this compound are the same. Okay, they're just drawn a little bit differently. But if I replace either one of these, I get cis-trans isomers or diastereomers. You see what I'm talking about?
A diastereomer is just one molecule, or what's the diastereomer?
Diastereomers are stereoisomers that are not mirror images of one another. Okay, they're not enantiomers. Because remember, that's one type of stereoisomer is enantiomers, which are mirror images. But either around a double bond or if I have multiple chiral centers, I can have isomers that are stereoisomers, but they're not mirror images of each other.
Well, aren't those mirror images of each other? The diastereotop, those first 2 molecules, the top one and the bottom one, right?
Yeah, they're not isomers. They're the same molecule.
Oh, right. Same molecule.
But if I replace either A or B with a hydrogen, then they are cis-trans isomers. Okay, but an example of kind of, I don't want to get too deeply into this. Remember when we had 2 chiral centers, and we had Fisher diagrams and all that? I could have another version of this. These are stereoisomers of one another, but they're diastereomers. They're not mirror images of one another. This can happen in this kind of a situation where I've got multiple chiral centers, also around double bonds. Double bonds can create the cis and trans isomers of one another are considered to be diastereomers. They fit into that general category. And that's what happens here. If I replace either A or B, I create a pair of cis-trans isomers, or diastereomers. So those hydrogens are said to be diastereotopic. Okay, they're incipient stereoisomers. That's simply replacing some imaginary group Z on their left. Now, what that means, what the heck does that mean? means A and B are not the same. That means they split each other. Okay, even though they look like they ought to be the same, but an even simpler way to look at this, which I probably should have shown to you,
Just don't spin.
is notice that type A is cis to the CH2Br. Type B is trans to it. That means that, and remember, we can't rotate around the double bond. They have different environments. And since they have different environments, they're different. And they will split each other. Does that make sense? And so we'll see geminal splitting between these two hydrogens in the structure, which will make it look a little more complicated. This is just a mental test to help us recognize that they really are different.
And the word diastereotopic only refers to.
It refers to hydrogens
Yeah, double
that,
bonded.
that are different from one another because they could be replaced with created diastereomers.
So even though this is diastereomer, for example, those hydrogens are not diastereotopic because they're not a.
Right.
Okay. All
They
right.
wouldn't be.
Okay.
Now, we do run into it around chiral centers. What I've got here is a substituted propane. I've got carbon here, a carbon here, and a carbon here. This carbon's got one chlorine and two hydrogens. This carbon has got this group, a hydrogen and chlorine. This carbon's chiral. Can you see that? Okay, now, the ones we're worried about here are these two, because these actually are diastereotopic. If I replace either one of them, okay, I create a chiral carbon. Notice let's put a Z group on it here. Then I've got a carbon that's got the rest of this molecule, a chlorine, a hydrogen, and a Z group. It now becomes a chiral carbon. And this also happens in this test. So I take a hydrogen off, put a Z group on there. If the hydrogen or hydrogens that are left are chiral, then they're going to split each other because they're literally different. Think of it this way. This carbon is chiral. So these two hydrogens next door to the chiral center will experience different environments from one another because there's a stereochemical difference next door. Okay, and so these two will in fact split each other, as well as split this hydrogen in a more complex fashion. It's almost as if there's two hydrogens. Well, it's almost as if there are different kinds of hydrogens next door. And so you'll see some complexity that we don't normally imagine. This thing, shown in a Fisher projection, is shown here, and you can see by replacing the Z's, I create chiral centers. Can you see that?
Am I the only one not getting it?
What's that?
And I don't get it.
If I take this carbon here,
Okay.
and it's
That
right
one.
here.
All right.
All right. Here's type A and type B. Here's the chiral carbon next door.
Okay.
And you can see its chirality. It's got four different things attached to it. However, if I replace either one of the HA or HB with a Z, I create a pair of isomers, diastereomers. Can you see that?
Right.
So,
So basically, it's going to let us know if we're just looking at that to try to figure out its NMR.
But
If we replace one of the hydrogens with the Z group, it's going to tell us if the hydrogens are going to split each other.
correct.
But we're really not replacing it with anything, we're just going to.
Right. Now, think of it this way, and it's easier for me to think of it this way. This is going to be a stretch, but I'm going to imagine I'm a hydrogen. Okay, and I'm attached to a carbon. And next door is a chiral center. And I've got a friend who's a hydrogen as well. And because there's a three-dimensional stereochemistry next door, I see a slightly different environment than my friend does. Even as we rotate, we see a slightly different environment. Now, if there are three of us there, then we're all going to be equivalent to one another because we'll all have a different, there's not a three-dimensional difference next door and on the carbon. Okay, and I don't know that that's easier for you to think, but that's exactly what we're doing here. Okay, now, what it means, bottom line, if you're looking at a molecule and there's a chiral center in it, there's a chiral carbon, you very often the hydrogens next door are going to be affected by this. Okay, even though they're not chiral themselves, they're not attached to a chiral carbon, they will behave as though they are. And so we're gonna see, anytime we see a chiral center in a molecule, we'll see complex splitting for both the hydrogen on the chiral center and the hydrogens next door. Not always, but very often.
Because there's three on the left and on bottom, they don't experience.
That's right. These three are equivalent to one another. But these two have a chiral environment here and a chlorine here. And so these two are in fact different from one another.
So if that chlorine was a hydrogen,
It wouldn't affect it. So it kind of has to be inside the chain, and it has to be next door to a chiral center for this to occur. And I think we've got the splitting pattern for this shown here. Now, the methyl group next door looks okay. All right, it's just a doublet. Okay, that's this guy right here. And it's got one hydrogen next door. However, this hydrogen is split by this hydrogen and by this hydrogen. And so instead of having it'll be a quartet due to that, and then it's got, there's how many hydrogens altogether?
Two.
Five.
So
3 for the methyl and 2 next door. But look at the splitting pattern for this. Okay, so this guy right here is right here, which we're looking at right here. So 1, 2, 3, 4, 5, 6, but look on top, each peak is split a little bit more. Right, the difference is that the two hydrogens are actually slightly different. And so I see kind of a messy looking multiple that's in general in line with my expectation, but that kind of looks like each peak like has a fork on the top of it because of this effect. But look, more importantly, look at these two guys. They're going to be split into a doublet by the guy next door, but they're going to split by each other. And so what we have here is a doublet on a doublet, like we saw before. Can you see that? Okay, these guys, let's look at this guy.
Right.
He's going to be split in a doublet by this guy, but that doublet will be split by this guy into a doublet on a doublet.
All right.
Okay, and so we're going to see a pair of doublets for each. Okay? Now, what this means, the bottom line is, because you're not growing up to be spectroscopists. What this means is if you see complex splitting, almost always it suggests this scenario. Either a double bond that's creating splitting on splitting, or a chiral center at the heart of the molecule. Does that make sense? So, even though it might be difficult, particularly with low quality instrumentation, to actually pull it apart this way, you should be able to look at that and say, this looks messy because I know there's a chiral carbon next door. Okay? Or, does that make sense? Now, some other issues that are part of our, will be part of the discussion is time dependence. Just as this bond is rotating rapidly, so these three hydrogens, which are identical to one another, experience the same average environment, the same thing will be true for cyclohexane. Because remember, in the cyclohexane chair form, you've got axial hydrogens and equatorial hydrogens. But the ring will undulate and flip-flop back and forth so fast that the axials will become equatorials and the equatorials will become axials so fast that they'll experience an average environment. And the hydrogens will behave as if we've drawn the cyclohexane ring planar, where each hydrogen is identical. We know from our past experience that this carbon here will be poked up or down depending on whether or not how the chair form looks, which will make these hydrogens either equatorial or axial. But this happens so fast that what we see is the average, and they will behave as if they look like that. Does that make sense? They'll behave as though they're identical. Okay? And that's due to the fact that the change, the rotation or the conformational changes that are taking place are so fast, relative to the time scale of the spectrum they run, we won't see a difference.
But wouldn't, it depends on temperature, so at a low temperature, would you see two separate?
Presumably,